We're gonna finish up Unit 6 today. We've got a number of students who are out at the career fair. There's a Minnesota Private College job fair down in the Twin Cities. So I know a number of students there. So I'm recording this for them and the online students. So I'll post this online in Unit 6 later on today. So we've been looking at this convolutional neural network stuff and how we can do some image recognition. We're going to try to do that with this learning activity. So we'll go through that today. And then we'll get you started on the project and see how that goes. So I'm going to just open up the learning activity. There's this notebook here. I'm going to open that up. And then it has a write-up that corresponds to it here that we'll look at.
Can you also go over what we need to post exactly from this?
Right.
In the session?
Right. That's a good point. So part of the thing for the discussion this week, one of the posts will be some details on and it should say Learning Notebook 6 there, but on how you're performing. And this is on 3 different network configurations, and we'll go the notebook's divided into 3 different parts. So we'll look at that today too. I'm going to just grab this out of here. And I'm just going to post that in Notepad for now. Okay. So, we'll be working with this Caltech 256 image database. There's and again, one of the things you have to do is just read a little bit about this database. And your first question is just to write a little bit about the Caltech image database. I wonder if I updated that link. The link in the write-up, I forgot to update. It looks like the link in the collab should be updated. They just change where this goes. So yeah, if I go here and click on this Caltech image database, this isn't just 256 images. There are 256 types of images, categories of images, and there's about 30,000 images in this. This is an extension of the original Caltech 101, which had 101 objects here. It's a huge data set. We are not going to do the whole data set because that would take us a long time to train and download here. So we are just going to do a part of the data set. So I'm going to get this started here. I'm going to run this. Now, in order to speed things up, this runs on a GPU. So I have this set to run on the GPU. I've just noticed that Google seems to have set a little tighter bounds. It used to be you could run one notebook on a GPU most of the time. You couldn't run more than one notebook, but now I've already hit some limit here. So let me know if you hit this limit. It says you can run it without a GPU, and that's what we're going to do. I'm just going to show you, rather than click on this button, what this means. Under runtime, there are runtime types. And this stuff will run a lot faster on a GPU. That's a graphics processor unit that's in the cloud. And again, it's the same sort of technology that's used in your video game machines. So on your consoles, and also if you have a PC that does you do a lot of gaming on, you probably have installed a GPU or have one on there. I'm going to have to switch this back to CPU. So mine is going to run probably slower, quite a bit slower than yours, but that'll be okay, hopefully. Okay, we're going to import our libraries. and we're gonna bring in this database of images. And what it actually is going to do is create folders of all the images for the categories. And we can display some sample images here of like dogs and stuff. But if I look in the left side in the folder, there's the CIS 3115 data. And inside that is the Caltech 256 database. And all we're doing is we're doing 20 categories here. So we're just doing 20 of these categories rather than 256 categories here, just to limit our time down. Now later on, when you want to like work on your project, if you want to do something bigger for your project, we can certainly have access to this, but we're just going to limit it to 20 categories for this. Okay, so we've got our sample images here, and we set up some callbacks. We've got to set up some image handling. So we've got to bring these images in from the different folders. There's a folder set up for each category. So you may have noticed like there's a folder set up for cowboy hats, and another one set up for dogs, and another one set for pictures of the Eiffel Tower here. So that is set up in a certain way so that we can read these in from each directory, and then each directory is its own category. So we have to do a little setup here for this. We're also setting this up so we have an image generator. Again, with these images, they have values between 0 and 255. We want them, neural networks work better if the input's between 0 and 1. So we're dividing all the pixels by 255 to get them in that range here. We can also do some tweaking to the images. So we could change them so that they're flipped horizontally, flipped vertically. We could just take a subpart, a cropped image down to a little bit or things like that. So there's quite a bit of different tweaks you can do to the images so they're slightly different each time. The only thing we're doing here is we're just flipping them horizontally. So it'll randomly flip it horizontally sometimes. And we just do that when we're training it. When we're testing it, we don't do that here. So this just sets up all of that sort of stuff. So it'll run. And then all of our images are going to be resized. These come with a variety of image size. All of our images are going to resize to 224 by 224 pixels. Now, there are 3 sections here, and I have them kind of minimized just so we can see the sections. Section 1, we're going to define our own CNN. That's kind of what we've done before. Section 2, we're going to use a predefined CNN with a lot of layers and simply replace the top few layers. And section 3, we're going to use a pre-trained CNN, and we're going to replace the top 3 layers, but we're also going to fine tune and try to train all the layers of this. So we're going to try out all 3, and then that's when you post to your discussion area. Those are generally the 3 networks we're going to do. You'll run this 3 different times, 1 for each section. So I'm just going to go into section 1. I'm just going to do it the way it is. So here's our network here. We define an input layer, a convolutional layer, a max pooling layer, a convolutional layer, max pooling, convolutional layer, max pooling here. Now, each time when we're doing this, after a max pooling, we're doubling the number of filters. So we started with 64, then 128, 256, 512 filters. Then we're going to flatten the image and send it through some dense layers. Here, instead of flattening it, we use something called average pooling, global average pooling, which is an alternative to that. And then we have our dense layers, and then our last layer is our softmax for output, and our output size is 20. We have 20 different categories. So this shows the layers. We start with a 200 by 224 by 224 image. It goes down to 222 by 222 because when we do our convolutions, we lose a pixel at the edges. We then max pool it down to 111 by 111. The next max pooling goes down to about 50 by 50. The next max pooling goes down to about 25 by 25, then 12 by 12. So at the end, we have 12 pixels by 12 pixels, but we have 512 different filters or features we're detecting there. We do our average pooling and set this down. So we end up with about almost 2 million parameters here. So that's a pretty big network for us, but we can set that up. So I can run this. And then I can train it. I'm going to train it here for 20 epochs, 100 steps per epoch. I'm just going to show this before I train it. The last time I did this, the accuracy started at about 7%, and it got up to 10, 15%, 18%, 20%, 25%. So I ended up at about 25% accuracy here. So that was this configuration. This default configuration after 20 epochs gets to about 25% accuracy. I want to try and make this better and or more accurate. So I want you to change this structure of this network here. Maybe you want to try fewer convolutional filters. Maybe you want to do more convolutional layers. So I could do both of those. I could say I want this to be 32, and I want to do 2 convolutional layers like that. And then this one, maybe I would want to do 64 or something like that and do 2 convolutional layers. Or do something else. Maybe I just do 3 layers here. Maybe at the end I'll do something. Maybe I won't have as many features here, or maybe I'll just do 128 features here. So try to change, add some layers here, try some stuff here. Some things we can do. We have convolutional layers, max pooling layers. We have dropouts and special dropouts. And again, we have these flattening and dense layers. Maybe I want to try more dense layers. So I would just say try 1 or 2 small changes to this. I'm going to run this and see how it looks. Now this shrunk it down. So it is just, it's less than 1 million parameters now. So that's kind of cool. Even though I added more layers, I have less filters at each layer. So now I'm going to try to change this and see if it'll get above 24%. So again, your job is to change up this. Now, there aren't any hard and fast rules for what's the best way to set up these networks. So again, generally people say more layers are better, more filters are better, but again, the size will increase here. So you can try different things for this and train it. And then keep track of your network structure here that you're going to use. So again, so this is not a pre-trained network. So we are training this from scratch. And you should track how much time it takes to do each epoch. Now, if you're on a GPU, it probably will take, how long is taking, like 30 seconds or less to do an epoch? Now, notice I'm not on a GPU. It is going to take me maybe 3 minutes per epoch. And if I do 20 epochs, that's going to take me an hour just to do this training. So hopefully you can run yours with GPU. It's going to be much faster. If we start running into issues with not enough GPU time, let me know. And we'll try to do it. It used to be you had so much a day, and so the next day you could try it out. So let me know how this goes. Google is known for changing these things frequently and not having a bit told very well. Okay, so again, we could see how much time it's going to take to do this. Note that the structure of my network. So again, I can just take, I could even just take this code here to show the structure. Later on, the structure we'll be using some pre-built networks, and so we can just name the structure. But here I'm just going to paste in the structure for this. The accuracy, again. Oh, or wait, what did I ask? So I defined my own here, and then we want to find the final accuracy here. Also, it's nice to note the parameters. So when you're putting in the architecture here, you might want to note how many parameters you had. So I had all my parameters are trainable. So I have total parameters is 784,000, and now they're all trainable. So again, I finally got my first epoch to run. It is running in 291 seconds. The training time is 291 seconds per epoch for 20 epochs. And 291 seconds is, what is that in minutes? 291 divided by 60. Yeah, 4.8 minutes. And again, yours should be quite a bit faster, hopefully, with the GPU. Okay, I'm going to stop this here, and because I have already done this, I'm going to go on and talk about the next section for this. So yeah, for your write-up, tell about this Caltech 256 database. Describe what changes you made to the starting CNN. Did you add layers? Did you take out layers? Did you change the size? Did you train more epochs? What did you try here? And then describe these parameters. How many layers, trainable parameters, total parameters, how long did it take? what's your accuracy on the training data and the testing data. And if you want, you can actually just take these answers and paste them right into your Brightspace discussion area. So I've been doing it over here, but again, you're welcome just to take, if you're going to fill out these answers, paste these in. We're going to do it for the 3 parts here. So you'll have 3 different ones. So this is just in step 1. Okay. So step 1, we're done. And again, you can look at your plot here. This looks like this is when I trained before on 20. It looks like it could maybe train. It still looks like it might still be going up. So maybe training a little bit more might help. It's hard to tell. Okay, so then we're going to do part 2. And for part 2, we're going to use pre-trained models here. There's a number of models out there that are pre-trained here, and they're pre-trained with what is called ImageNet. So when we load in these models, we'll say, like, we'll start with a pre-trained model and we'll list it. And there's different ones like VGG16 or Exception or ResNet 50. And then we'll load in the weights that are pre-trained with something called ImageNet. So what is ImageNet? So if you go into your write-up and look at ImageNet, ImageNet is a large database of what used to be an ongoing challenge of images. 14 million images, hand annotated by the project here. So with bounding boxes, over 20,000 different categories here. So like things like balloon and strawberry and things like that. So it's a huge database and has been part of for many years was a well-known image challenge for this that was developed here. So these models are pre-trained with this large database here. So that's why, like here, when we run this, what we do is we're going to pick one of these. Now, which one should you pick? There are some common architectures you could read about here. So AlexNet was the first convolutional neural network. We kind of looked at that earlier on Tuesday. VGG16 and VGG19 were also pretty common early networks, and that's the default here is we just say in our code, we say, again, one thing to note is some of this is in green and it has a pound sign at the beginning. Let me bring this up a little bigger. How about? So the lines that have a pound at the beginning of them are commented out. They're not going to run. Only this one that's black that doesn't have a pound is going to run. So the only thing that's going to happen here is that we're going to load in VGG16. If we want to load in a different network, we could comment that one and uncomment another one. Let's say we wanted to do MobileNet v2. I would uncomment that. And now this is what will be run, is this one. So again, you want to select one of these. And you can read a little bit about some of these over here. So like here's VGG16, VGG19. ResNet has these skip connections and all these things, and they're set up in different amounts of connections here. So like ResNet 50 will have 50 layers here. Inception have these special blocks called inception blocks, and I think we looked at them last time, where again, you feed into these filters that feed into, they divide the input to multiple filters and it goes back. So we have this sort of base feeding into these filters and they go to other filters, and then there's all concatenated back together here. So that's inception. Models do that. DenseNet, you can read a little bit about how DenseNet works and how it tries to do multiple things. And again, or else you can just try one of these other networks here. This article also talks about some other top pre-trained models. So pick one of these models. I'm just gonna, and then train it, go down here and get it to run. I'm just gonna run this. And it'll load up this network. It'll tell you like, it's got, so the base network here has 2 million parameters and none of them are trainable. And then I add on some stuff to this. I add on my own dense layers. So I end up with having almost 400,000 trainable parameters here for this, but a whole bunch of non-trainable parameters. And then we can run this and your accuracy should get very fast. Last time I topped out at around 23%. This time I'm at 23% after the first one, and I get up to 94% here. So again, I can try to do that now. I'm not on a GPU, so it's going to be slow again for me. But since this is a small, much of it's pre-trained, I don't have to train it. Training will go a lot faster here. So, a lot faster. So let that run and see how good. Now I'm going to go up and talk about this code a little bit. So what are we doing? What's the code? So again, we're picking one of these models. Pick one of these, and the default was VGG 16, which is the oldest model here. And I think all of these should run better than that. We're going to say the pre-trained model is not trainable. Okay, so we're not bringing it. And when we bring it in, we're going to say include top, and we're going to say false. So this network has a bunch of layers starting with the input and going up to the output, which is called the top here. And we're going to skip the output layers, which are the final dense layers. And so we're going to add our own dense layers to the top. So it says the output, include output is false. So it'll give us our network, except it'll cut off the top 2 or 3 layers, the dense layers. So once we have that pre-trained model, we're going to start with that. And then we're going to add global average pooling and then a couple dense layers. And then our final output layer here. And then do our summary. So now I can do that. And again, you can then see how many layers there are in some of these networks. What am I doing? I'm doing mobile net v2 here, and it just has layers after it's just got hundreds of layers, maybe not 100, maybe, or it looks like it has at least 100 layers. Okay, maybe not. Well, it has a lot of layers. So again, this whole structure is here. And again, if you want, I don't have articles on all of these, but again, I'm doing, which one am I doing? MobileNet v2. I could just Google MobileNet v2 and look at what it's like. And what it's set up to do here. Okay, so your job is to select one of those layers, run it. Here again, if you wanted to change the number of dense layers here, you can. I have this set pretty small, so if you really want to increase accuracy, it's not uncommon for these to be 1,000 by at each dense layer or something like that, or at least 1,000 and then 256 or something like that. But to speed up training, 256 seems to work pretty well. Okay, and then we'll go here and run this.
So on some of these, is there an easy way to see like how many layers there are? Like
No.
or okay.
So it's
It's on the post, it says we need it, but I use the efficient net one.
Right. I would say I'm okay if you say like more than 3. I'm wondering if Bard or something will tell us. So did anyone find so
I tried,
how many?
I tried ChatGPT and it
Yeah.
said 19, but
No, there's more than that. Yeah, that's just so this one says mobile V2 has 53. But then I don't know if that means 53 blocks here, and then each block is like 3 layers or not. So again, I don't expect you, if it's more than 30, if you count more than 30 and you don't know how, you can say more than 30 at that point. So yeah, that's a good question. Okay. And again, we can look at our graphs. And again, this is still, if I look at the blue training graph, this one did 20 epochs and it's still going up. I think this could get better if we trained it more, trained it for 50 epochs. It'd be interesting to see how accurate it did. Okay, yeah. Some of these pre-trained ones get there very fast here. So okay, so your write-up describe the ImageNet data set, which these are all trained on. Once you select a CNN in Keras, find at least one article that describes it. So again, Google it or something like that, and find an article that talks about it and get a description of that architecture here and then cite it. I'm fine. This isn't an official paper, so if you want to cite it, if it's a paper and you want to cite it in APA format, that's just great. But if you just want to have the URL for something like this, I'm fine with that. Later on, like when we do the final paper in this course, we'll have to do APA citations and stuff like that. But for an assignment, I'm fine either way. And again, then put in your results. What's the name of your pre-trained model? How many layers? And again, you can estimate for larger networks here. Trainable parameters. So again, in your network, you should see, oops, wrong way. The first network displayed will have no 0 parameters, but the second one will have like mobile net here, and it'll list that. And then, so this is when we want the total parameters. The total parameters should be in millions, and the trainable parameters should be often less than 1 million. So here's my total parameters in that. So again, and let's go back to this picture. So here's what we're doing here. So we've got this like VGG 16 here, and we are getting rid of the top layers, the fully connected layers and the softmax layer that were originally trained, because they were trained on ImageNet and not on ours. But all these other convolutional layers are detecting features and creating these feature maps. So we're using that, and then we're adding our own fully connected 256 layer, another fully connected 256 layer, and then a softmax. And this is all we're training, is these top 3 layers. And the rest of it is fixed for this. And we'll see this when we get the language models, 2 large language models. We'll be able to bring in a large language model and just train something on top of the large language model if we want. Okay, I'm going to stop this. Yeah, I'm getting up to so my accuracy on the training data is getting to 100%. the valuation accuracy, the testing accuracy is only at 98% here, and then it's actually getting a little worse there, so it's interesting. Okay, the last thing we want to do here is part 3 is we're going to do the same thing. We're going to take a model, cut off the top, and add some new layers at the top. But we're also going to allow all these other layers to be trained. We call that fine tuning. So we'll fine tune all of these features so that maybe if we have some features that are detecting like spots of things, you know, on dogs and cats, and we're really just looking at whale spots on whales now, it will probably tweak that filter so that it works better on whale spots rather than dog and cat spots or something like that. So we're doing the same thing here. We're selecting one of these pre-trained models. We're uncommenting one of these. You know, I'm going to do this one. So only one of these should be commented. So you can see this one is in black, the other one's in green here. And notice now pre-trained models is true, or trainable is true. So we can train this model. We set it up the same way, but the layers, total parameters is 2 million and the trainable parameters are 2 million. So now when we train this, it's going to train slowly here. Okay. So it'll go kind of slow in the whole training stuff. But you would think with fine tuning, it should refine itself and maybe be even more accurate. So your question is to see if how long it trains and does it get to be more accurate as we go here. We want you to report your final runs here, do some analysis, you know, look back at them, tell me which one was, you know, was the slowest to train, what was fastest to train, what was the most accurate. So do a little bit of analysis on this here. Now, I'm just going to mention a little bit about writing in this class. We haven't talked too much about writing. At the top of Unit 6, there's a unit on writing data analysis. So some suggestions is know your domain here and know your audience. And largely you can imagine your audience for the assignments and stuff are people in your class, your peers or me. Okay, so you can talk about the data set, and you maybe think of it like as a classmate who missed class this week. And your write-up is supposed to bring this person up to date on this. Or me, and you want to show me that you understood what was going on this week. So things like the problem domain, what do we know about the problem domain? What do we know about the data set? What do we know, how do you analyze this? So again, you should be describing, when I ask you to describe the data set, try to give some details out. Just don't say, oh, it's this data set, it's the MIMS data set. I want you to provide some detail in case that person or that your audience doesn't know what that is. But again, you should know, be somewhat familiar with, like someone in this class as far as the audience goes. And later on, we'll talk about other audiences. So again, for your weekly write-ups, assume the audience is your fellow teachers or students here. For projects, might want to expand this to maybe someone who's less familiar with this sort of stuff. So also things like presenting numeric results. I often will say things like a paragraph. That just means like the kind of level of detail, a page versus a paragraph versus a sentence. But when we're presenting numeric results, you can use graphs, do this sort of stuff. You can create a graph, create a table and display this stuff, do a simple table or something like that for this. Also watch your digits. So like a lot of times when we're putting out this accuracy, it is saying we're at like, look at one that has some accuracy here. And the accuracy would be like 0.9760. Well, I'm not, but it jumps around a lot. I want you to just think about significant digits here, and we're not going to do a lot of analysis on it, but generally you should be limiting yourself. Nothing we do has more than 1 or 2 significant digits. So you can talk about 92% or 92.3%, something like that. Here, you don't have to, and it's not good to list long accuracies that suggest that those are important or significant amount of accuracy, and in our examples they are not here. When we run it again, one thing to think about is if you ran it, quit, run it again, how much different would these results be just given the randomness or stochasticity in our models, in our simulations. So and then I give some examples of good analysis here and poor analysis. Now you can use ChatGPT sometimes to help with this. ChatGPT tends to be wordy on some things, so just try to narrow it down or give it some examples here. When we're later on, we'll actually look at better ways to use these language models when we get into them. But you can use that if sometimes help you with, or to fill out this analysis here. Okay, so yeah, that's what you're writing. You're doing some analysis. The last thing I just want to mention is, these models are pre-trained, like with the ImageNet database. There are issues with bias in data sets. And so one of the things we run into is that when we're using pre-trained models, it's important to know how they were pre-trained, what data they were pre-trained, and if there was bias in the pre-trained data here. And because that often, even though we're fine-tuning the training and doing that sort of stuff, there can be bias in the images used in the pre-train here. And we see the same thing for large language models. There can be bias in these large language models. So whenever you're using a pre-trained network, you should be aware, you should be considering bias and the data that it was pre-trained on. So, okay. So you've done this, you run 3 again, and if I'm just going to minimize this again so we can see the 3 sections again. So section 0 is the setup. Section 1 is where you create your own CNN. And then section 2, you do a pre-trained model, and we just train the top layer. Section 3, we do a pre-trained model, but we fine-tune it and retrain the whole thing there. And these are the 3 things generally I want you to post in your discussion for this week. So again, you can just take from your write-up, you can take each one of these here and you can do 1 post or you can do 3 posts here, but just post those to your write-ups there. Questions on this? So I'm gonna talk about the project and see and make sure you're ready to go, and then I'll let you keep going on both of these. For the project, we're gonna try to get a little bit more into what the scientific kind of process. This course covers the natural science outcome, and so we like to look at some of this from kind of a scientific perspective using a scientific method. And one thing, and we'll talk more about this when we get to like the final project, but at this level, what we basically want to be doing is make a hypothesis and test that hypothesis out here. So we're going to make a hypothesis about some way to improve our network, and then we're going to try this out and see if this works or not. And you can make a hypothesis, like maybe you'll say creating a custom convolutional network should work better than a pre-trained network because I can customize it however I want. So that might be your hypothesis, and you'll test this out. You'll create one, and you'll use a pre-trained one, and you'll see which one's better. And that would turn out to be false. The pre-trained one is almost always better than the one you made from scratch. But that's okay. That's a good result. It's fine. There's no reason why you can't make an hypothesis and show that hypothesis is wrong there. Now, there are a lot of sometimes that will go back and retrofit their hypothesis and change it to the other way. And you can, if that makes you feel fine, you can go back and do that there. But our idea is that have a plan, test it out, and present the results here for this. Now, in order for this to work, we really want to try to keep everything we can consistent and only change one thing that is in our hypothesis. So if we think more training will make it more accuracy, we should leave everything else the same and just do more training, longer training here. If you think more layers will make your network work out, you should add more layers, but keep the training and everything else the same. You should not add more layers and do more training and say that because then you don't know which of those two actually helped. So we want to try to be hold a lot of everything we can. We want to hold it as constant or unchanging as possible and only choose one variable that we're going to change that's in our hypothesis. So again, there's some possible hypotheses here. Adding dropout layers will improve this. Doubling the training epoch will train this. Using one pre-trained network is better than another. Maybe you think, mobile net, since it's newer, will outperform VGG16. That's a hypothesis. So you want to state some hypothesis. You then are going to test it out and write about it. Now you have two different data sets you can choose from. The humpback whale data set here. This comes from a Kaggle challenge from this there's this Happy Whale group, and they've been around for a while. They've been promoting a number of different changes, and in fact, there have been 3 or 4 different whale tail kind of identification challenges on Kaggle here. So this one is an older one from 2018. There's been newer ones here, but there were almost 600 different teams or people competing for this one. And there's good prize money for this one, if I remember correctly. So again, you see humpback whales, and we want to, we see their tails. We're going to identify their tails and we do that. Now, the actual data set for the humpback whales is really large. And again, would take us a day, probably 20 hours to train. So because it had 1,000 whales or more in it, I've cut it down to a smaller data set here. So I've selected the top 200 whales with the most images. One of the problems with the original data set is there were quite a few whales that only had 1 or 2 images, and it's hard to train when you don't have that many images. So you have to use kind of a different setup than what we use. But so that's why we're just doing the top. So it's the most popular whales that are out there. These are the Instagram whales, the 200 Instagram whales that are out there that everyone follows. So that's it. The other thing is do the X-ray images data set, another Kaggle challenge. Again, they're trying to look at X-rays and determine from an X-ray if someone has pneumonia or not here for this. So again, the network structure is similar. You can choose any of these built-in networks. You can set trainable to true or false. Do you want to fine-tune it or not? You can add layers to it. If you don't want to use one of these pre-trained layers, you want to do your own, you can just uncomment this stuff and build your own network here. You can change how long you train it. So just think of something you want to test out that you think might improve it and try it out. And then your write-up, everyone does the same write-up for no matter what data set you're. So one thing you have to do is describe the data set here, describe your hypothesis, and I try to do it in a paragraph or two, provide some details on it. Why are you making this hypothesis? Why do you think this will improve or affect the results? And what made you think that? Feel free to, if you want to do a little research on this, you can always just Google, will more layers in a CNN improve performance? And find, there'll be sources that'll talk about that. So see if you want to do that. Run your experiment. Again, changing just that one thing and then analyze your results here. Questions on the project for this week? Okay, I'm going to stop here.